Hello, everyone. Thanks for joining us today. Welcome to today's webcast brought to you by Power Engineering Magazine and E1 Utility Systems Generating Solutions. I'm Russell Ray, Chief Editor of Power Engineering Magazine, and your host for this hour. Today's event, Hydrogen Safety, Best Practices for Securing Your Most Valuable Assets, will be presented by our expert, Gus Graham of E1 Utility Systems. A PDF of Mr. Graham's presentation will be available to our audience. You can access that PDF, that presentation, by clicking the Event Resources tab on the console in front of you. But before we move on to Gus's presentation, I'd like to share a few housekeeping details with our audience. This webcast is both live and interactive. So you can ask a question at any time by clicking on the Ask a Question button in the presentation window. We'll begin the Q&A after our speaker has completed his presentation, but keep in mind you can submit your question at any time during the webcast. If you are running pop-up blocking software, you will need to disable it to view this webcast. In addition, it is recommended that you close down all other applications for better performance. For your convenience, this webcast will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from the home page at www.power-eng.com. Well, now it's time to introduce today's speaker. Gus Graham is the Director of Products and Markets for E1 Utility Systems in Africa and Asia. Mr. Graham also served as Director of Engineering at E1, where he led product support and new product development. Before joining E1, he held several management positions over 8 years at Plug Power, where he led efforts in the product development of stationary fuel cells. He began his career as a development engineer at Foster Wheeler Development Corporation. He has a wealth of knowledge and experience. We're very lucky to have him here with us today. Doug, welcome to the webcast.
Thank you very much, Russell. Hydrogen's use as a cooling medium in large turbo generators used in the power industry dates back to the 1930s. In this presentation today, we'll discuss why hydrogen was selected and review the best practices for ensuring the safety of the staff and equipment working and operating in this environment. We'll begin by reviewing why hydrogen was selected. We'll review the properties of hydrogen and the hazards associated with working with hydrogen. We'll discuss hazardous areas and the equipment design and processes necessary to ensure safe plant operation in this environment, including an overview of the key elements of a safe generator purging process. I'll give an overview of the different types of hydrogen purity monitoring systems and review additional generator monitoring equipment. And in closing, we'll review hydrogen leaks and leak detection methods. Back in the late 1930s, increasing demand for larger generators required alternate cooling methods to be developed. These larger generators required a more efficient cooling method. They were looking for a low-density gas with good cooling properties, and initially helium was selected. Due to the scarce supply of helium and the relatively high cost of helium, hydrogen became the gas of choice. Hydrogen provides less windage or frictional losses in the rotating rotor of the generator. That's because at generator operating pressures, the relative density of hydrogen is 4 times less than air. Hydrogen has better heat transfer characteristics than air. Hydrogen is 14 times more efficient at removing heat than air. That is to say, 1 pound of hydrogen will remove 14 times more heat from a given environment than 1 pound of air. For the equipment manufacturers, this all equates to more megawatts per pound of iron. Some additional facts about hydrogen as a use as a cooling medium. Hydrogen-cooled generators are a sealed environment which prevent contamination within the generator. Hydrogen-cooled generators are also pressurized vessels. The increased pressure suppresses the partial discharge phenomenon and increases the level of voltage required for component breakdown. A pure hydrogen environment prevents oxidation. This allows generator manufacturers to select lower-cost materials when designing the internals of a generator. Pure hydrogen does not support combustion. Currently, there are more than 10,000 hydrogen-cooled generators operating worldwide. For all the chemical engineers in the audience, we'll review some of the properties of hydrogen. This is right out of Praxair's safety data sheet. Hydrogen is a colorless, odorless, and tasteless gas, which makes it undetectable by human senses. Hydrogen is non-toxic, but it can be suffocating by removing oxygen from confined spaces. Hydrogen is not a carcinogen. It is the lightest gas, which allows it to diffuse readily in air. It's non-corrosive, but it will reduce the mechanical properties of some metals, resulting in embrittlement. Hydrogen burns with an almost invisible bluish flame, which makes it very difficult to detect during daylight conditions should there be a leak in any of your hydrogen auxiliary equipment in your power plant. The explosive limits of hydrogen are the widest of any combustible gas, ranging from 4% to 76% by volume in air. And the auto ignition temperature in air is very high, 566 degrees centigrade or 1051 degrees Fahrenheit. So if you had a combustible mixture of hydrogen in air, you would have to heat it to 566 centigrade for it to catch fire or cause an explosion. Most people are familiar with the elements necessary for fire, represented here by the fire triangle, where you have air plus a fuel plus an ignition source, and that will result in a fire or explosion. Today we're going to introduce you to a concept of a safety triangle comprised of the right equipment, the right processes, and the right people to yield a safe plant operation. In addition to the inherent risks of working with a flammable gas such as hydrogen, following are some additional risks we're being faced with in the power industry. The fleet is getting older and being asked to operate beyond the original life expectancy. Hand in hand with that, the associated hydrogen auxiliary equipment is getting older and potentially outdated when compared to today's industry standards, which we'll discuss a bit later on. The workforce is getting younger and leaner, and compounding this, the training and apprentice programs that are available today aren't what they were even just 10 years ago. And lastly, the outages are getting spaced further apart to maximize runtime. This places additional stresses on the equipment and staff. Even well-designed and maintained generators can become compromised by these serious operational challenges. We know if proper standard operating procedures are not followed, you can have some very serious problems, including equipment damage and loss of life. In this instance, there was a failure of the collector end seal due to a turbine rotor imbalance. This led to a leak into the exciter, a hydrogen leak into the exciter. We had all three conditions of the fire triangle being met, and that led to a fire and an explosion occurring. Luckily, there was no loss of life as a result of this event. Now we're going to review the specifics of hazardous areas in the power station, the equipment that's designed to operate in these areas, and the important processes necessary to ensure safe plant operation, our safety triangle. So to begin with, hazardous areas are places where concentrations of flammable gases, vapors, or dusts can occur. These hazardous areas are classified based on the risk of an ignitable concentration forming in the hazardous area. These hazardous areas can also be referred to as classified areas. An area classification refers to the rating applied to the area based on the risk of a flammable concentration occurring in that area. These area classifications are the responsibility of the power station to define, and this typically occurs during plant design phase. Prior to the mid-20th century, power plants weren't required to define area classifications, and we found during retrofit and upgrade opportunities this has led to some confusion because power stations aren't even aware of what the hazardous area classification is for their hydrogen auxiliary equipment. These hazardous area classifications are broken down into 3 zones as they're referred to. A Zone 0 area is an area where a flammable mixture is present at all times. A Zone 1 area is an area where a flammable mixture is sometimes present during normal operation. And the last zone is referred to as Zone 2, and this is an area where a flammable mixture is present only during abnormal conditions. These Zone 2 areas are the applicable area classification for most of the hydrogen auxiliary equipment in your power station. The illustration on the screen here is an example of an equipment OEM defining the Zone 2 area created by their piece of equipment. That is to say, within this piece of equipment, there's pressurized hydrogen in the pipework and in the instrumentation, and as a result of that piping, there is a risk of a flammable mixture occurring during abnormal conditions in the hashed out zone that they've illustrated by this picture. These are the drawings that are used by the power stations as part of the plant hazardous area assessment for defining the different zones and classification areas in their power stations. The image here is an example of a power station defining and marking the Zone 2 area in their power station. You can see here they went as far as to erect a barrier to limit access to the area, and they've used that barrier to also use as the markings and signage to appropriately warn individuals of the area and what hazards are present and safety precautions that need to be taken. Now that we have an understanding of hazardous areas, let's review the equipment design requirements for these areas. So as you can be sure, hazardous areas require specialized equipment. You can't just run out to Napa or McMaster Carr and purchase a piece of equipment and install it in a hazardous area. The equipment needs to be designed to operate in the respective area classification for that installation. In our case, for hydrogen use, the markings on the piece of equipment would carry Roman numeral 2, the letter capital B, plus H2 for hydrogen, or the Roman numeral 2 and capital C. Either of those markings are appropriate for equipment to be installed in a hydrogen, an area that's classified for hydrogen. Equipment that's designed to a more strict area classification can also be installed in a lower classified area. So if you've got a piece of equipment in your power station that's designed for a Zone 0 area classification, it can be installed in a Zone 0, a Zone 1, or a Zone 2 area. For a piece of equipment that's designed for Zone 1 application, it can be installed in Zone 1 or Zone 2. And for a piece of equipment that's designed for a Zone 2 area, it can only be installed in a Zone 2 area. So within the design of the equipment, there are different protection principles that are applied by the equipment manufacturers to meet the hazardous area requirements. These protection principles will vary from equipment OEM to equipment OEM and from device to device, depending on the characteristic of the equipment. The first principle that we're going to review is a piece of equipment that has no arcs, sparks, or hot surfaces. Within that principle, there are two methods that are applied. One is referred to as increased safety, and a piece of equipment that is marked for increased safety will carry the small letter E. The second method that's employed is referred to as non-sparking, and a piece of equipment that's designed for non-sparking would carry the letters NA. In the image on the screen here, we have an example of a Type E protection principle. That's the metal enclosure. It's a Type E enclosure with a non-sparking piece of equipment installed in it, which is illustrated here by the power strip. The next protection principle is to contain the explosion and extinguish the flame. There are three methods within this principle, the first one being referred to as flame-proof, and the equipment that is designed for the flame-proof method is marked with the small letter D. The next method is powder-filled. A powder-filled piece of equipment will be marked with the small letter Q. And the final method is referred to as enclosed break, and that piece of equipment would be marked with the letters NC. The most common method we run into in this principle is a flame-proof. Illustrated on the screen here is a flame-proof enclosure where the equipment manufacturer will install all of their equipment that is not rated for use in the hazardous area. And to the right of the image there, in the red tag, is the actual equipment marking for that piece of equipment. And that equipment marking, as you can see, has the EX for explosion-proof, the small letter D, and the letters 2B plus hydrogen, as we were referred to previously. The next principle we'll review is referred to as where they limit the energy of sparks and the surface temperature. There are two methods within this principle. The first one is intrinsic safety. Equipment marked for intrinsic safety would carry the small letter I, followed by the letters A, B, or C. There are three sub-methods within the intrinsic safety design concept. Limited energy is the other method. A piece of equipment under that concept would carry the letters NL. Protection principles such as intrinsic safety and limited energy typically require two pieces of equipment to meet the overall requirement for that principle. One piece of equipment is installed in the hazardous area, and the second piece of equipment is installed in the general purpose area. For the image that we have on the screen, we have a dew point sensor and the corresponding barrier or safety shunt that matches up with the dew point sensor. The dew point sensor is installed in the flame-proof or the hazardous area, and the barrier is installed in a device such as the flame-proof enclosure or in another general purpose area. Last protection principle we have to discuss is where they keep the flammable gases out of the area in question. And there are three methods within this principle. The first one being pressurized equipment. Pressurized equipment will be marked with a small p followed by the letters X, Y, or Z. There are three sub-methods associated with pressurization. A restricted breathing apparatus would carry the letters NR. A piece of equipment that is protected via encapsulation would carry the small letter M followed by the letters A or B. There are two sub-methods within that encapsulation method. And then an oil immersion method would carry the letter O. Two of the most common methods that we run into for this principle are encapsulation and pressurization. The image on the left is a picture of a solenoid valve where the coil, the protection concept employed here is encapsulation type B, and you can see the marking on the equipment is EX, MB, and 2C for the hydrogen environment. The image on the right is a piece of pressurized equipment. So all of the equipment that is of concern is within a metal container that is pressurized with air. And the principle here is if the container is pressurized, any of the flammable gases that would be in the area around it could not enter into the metal container. Pressurization usually has multiple pieces of equipment associated with the concept. There's a regulator to limit the flow of air into the equipment, usually a pressure sensor to monitor the differential pressure between inside the equipment and the ambient air, and then some form of electronics that detect the lack of pressure and isolate the electrical power to that piece of equipment should there be a loss of pressurization. All the material I've just covered is intended to provide an overview of hazardous areas and the equipment designed for these areas. There are specific courses offered through notified bodies such as Intertech, FM, and UL that go into a lot of detail on this topic, and these courses are highly recommended for plant personnel that are responsible for hydrogen-cooled generators and the associated hydrogen auxiliary equipment. Now let's review some of the processes related to working in these hazardous areas. So as you can be certain, the risks of hazardous areas require precaution, and operator training is the most critical element of safe plant operation. Adequate signage identifying the hazardous areas and what safety precautions need to be followed is also very important, as we illustrated on the example a few slides ago. Adhering to the OEM prescribed maintenance intervals and the maintenance processes on all the equipment operating in the hazardous area is also very important. Using qualified EX certified maintenance personnel for equipment in hazardous areas is a good best practice. As I mentioned a couple slides ago, there are specific courses that are offered that you could have your staff at your power station attend, or you could request that the personnel coming to do maintenance on your equipment present the proof of their certification to that standard. Regular calibration of your hydrogen purity meter is obviously very important. Strict adherence to the generator purge procedure, and we'll have a little more discussion on that in a moment. And then the use of only spark-free tools in the hazardous area is also a very important best practice for hazardous area processes. And again, these are examples of the critical elements that comprise safe plant operation when working in hazardous areas. One of the most critical processes associated with hydrogen-cooled generators is the generator purging process. As I mentioned earlier, outages are becoming less frequent, and as a result, plant personnel may not have had any experience purging a generator when the time comes for their generator to be purged. Having a good, solid purge procedure and associated equipment are critical to safe plant operation. So it begins with an updated and understood standard operating procedure. Hand in hand with that, having a current and accurate P&ID of your hydrogen auxiliary equipment is very important. If you've made any improvements or modifications to your hydrogen auxiliary system, ensuring that those updates have been incorporated in the P&ID and the SOP is very important. Along with that, verifying that all the valves and equipment are properly labeled and agree with that updated P&ID to make it clear for your operators. Verifying that your hydrogen purity meter is calibrated and operating properly. And associated with that, if you're using a portable gas analyzer for your purge process, ensuring that that is also calibrated and operating properly. The use of portable hydrogen sniffers is recommended, as well as the old standby liquid leak detectors such as Snoop or SOAP. Personal LELs, or lower explosive limit detectors, are also recommended for all the operators working in the hydrogen area. You mentioned the use of non-sparking tools made of a material such as bronze. Ensuring that you have sufficient carbon dioxide present in the plant to purge all the generators on site. So if you're a power station operating multiple generators and you're doing a purge process on one of those generators, it's important to have appropriate volume of carbon dioxide present to purge all the generators should there be an event during the purge process of the generator you're working on. Having signage available to note which gas is in the generator. Having a keyed lockout for the air and hydrogen supply system, also very important. It doesn't ensure that air and hydrogen won't be admitted to the generator, but it certainly goes a long way to mitigate that risk. Communicate, communicate, communicate. As we know, communication is usually the key point that leads to breakdowns, and we can't stress that enough. And including your operations team and your INC team together is also a very good best practice. Portable gas analyzers, such as this model, can be critical to ensuring the most accurate and conservative gas purity measurement is used to decide when to switch to the next gas in the purge process. During the generator purge process, valves and pipework that haven't carried gas potentially in several years will be in service. The condition of the valve packing and tube and/or pipe joints may be suspect. The use of handheld hydrogen leak detectors such as this model are important tools to ensure the safety of the personnel working in the environment and for detecting the need to repair or upgrade worn-out valves and pipework. As with the handheld leak detector, the personal LEL detectors are critical safety devices for the personnel working in the hydrogen auxiliary system area and in and around the generator. And again, here this image illustrates some of the non-sparking tools. The use of these spark-free tools is vital to ensure the safety of the personnel working on and around the generator and hydrogen equipment. So now that we've safely purged and filled the generator, let's discuss one of the most critical pieces of equipment on your hydrogen-cooled generator, which is your hydrogen purity monitoring system. Online hydrogen purity monitoring is mandatory on all hydrogen-cooled generators. There are two primary methods for measuring hydrogen purity: density meters and thermal conductivity meters. Now, there are pros and cons to the design principles of both, and different techniques are applied by the purity meter OEMs within each measuring method. It's important that as a plant operator, you know which type you have, you know that it is maintained per the OEM recommendations, and that it is operating properly at all times. Now, the different generator OEMs integrate the hydrogen purity meters into skids or cabinets that are referred to as hydrogen control panels or hydrogen control cabinets. Internationally, they're also referred to as hydrogen cubicles. These installation types can vary greatly from generator OEM to generator OEM and from plant type to plant type. Knowing and understanding the specifics of your plant system is vital to safe plant operation. Lastly, the type of seal oil system on your generator also impacts the hydrogen purity system. A vacuum seal oil system will employ a closed-loop style hydrogen purity monitor where the hydrogen is constantly circulated from generator fan pressure to generator fan suction, and the purity meter is measuring the case purity at generator pressure. These systems employ a bleed and feed style system for maintaining generator pressure and purity. Scavenging seal oil systems employ an open loop style system where a small amount of hydrogen is constantly vented from the generator's seal drain enlargement tanks to maintain generator purity, and generator pressure is maintained via a make-up hydrogen regulator. In these systems, the purity meter is measuring the purity of the gas in the headspace of the seal drain enlargement tank and can be measuring at generator pressure or at atmospheric pressure, depending on the configuration. The image on the screen here is an example of a vacuum seal oil system utilizing a density blower method of hydrogen purity measurement. You can see the different pressure transmitters that are there that are measuring case pressure, fan differential pressure, and then the associated differential pressure generated by the fixed speed of the density blower. The image on the screen here is an example of a scavenging seal oil system, which is utilizing a thermal conductivity method of hydrogen purity measurement. And you can see the different, this is a very old piece of equipment. It has the meters that indicate the purity as analog devices, pressure gauge for case pressure, and the flow indicators that indicate the scavenging flow of hydrogen leaving the panel going to vent to maintain the purity of that generator. And these are just two examples of a very large variety of hydrogen purity systems that are in use today. Online monitoring devices are also important tools to assure reliability and optimum performance of your generator. As risk factors increase, additional monitoring becomes necessary. This simple graph depicts the risk versus level of monitoring relationship. Different generator OEMs provide a basic level of monitoring unless otherwise selected by the utility during plant construction. As risk factors in the fleet or plant increase, additional monitoring becomes necessary. Some of the risk factors used for this evaluation include the age of the generator, the size of the generator, the criticality of the generator to the local grid stability, and the level of experience of the operators, and the overall plant staffing levels. Some of that additional equipment that's available include additional temperature sensors that can be installed within the core itself, at the back of the core, or in the stator cooling water system for those with generators with water-cooled stators. Again, those additional temperature sensors will be monitoring for hot spots and other overheat conditions. A flux probe can be installed and used to detect shorted rotor turns. A generator condition monitor can be installed and used to detect the early stages of generator overheat and arcing. Additional vibration sensors can be installed on the end turns or along the frame to detect loose core wedging or rotor imbalance due to hot spots or shorted turns. High dew point related failures such as retaining ring failure and insulation breakdown can be prevented with online dew point monitoring and the use of hydrogen gas dryers. And rotor shaft voltage monitoring can be used to detect voltages that could result in current discharges and electrical pitting on the rotor surfaces. Again, these are just some examples of additional online monitoring equipment that can be used on your hydrogen-cooled generator. Because the generator case is pressurized, there are numerous locations where hydrogen can leak. Some examples are the hydrogen coolers, the rotating hydrogen seals, and any piping connection, flanges, or bolt-on inspection covers. Hydrogen leaks can also occur in auxiliary equipment that is connected to the generator. The allowable daily leakage from the generator is always specified by the manufacturer and is determined by the hydrogen usage. The hydrogen usage is either monitored by the simple method of counting the number of bottles consumed on a daily or weekly basis. Some generators have online mass flow totalizers that actively measure the hydrogen usage. There are different methods used for leak detection. Some examples are the good old standby, such as liquid soap or Snoop. You can use ultrasonic leak detectors, handheld leak detectors, such as we illustrated earlier, or infrared leak detection method. Although hydrogen dissipates quickly in air, it is important to also be aware of areas near and around the generator where hydrogen can trap and accumulate. A best practice for hydrogen leak detection is to use a detailed pictorial guide to show personnel where to inspect for hydrogen leaks. And all plants should have a well-written procedure on locating hydrogen leaks. The image on the screen here is an example of a generator bushing penetrating the generator case. Potential leak points here are the flange itself, where it bolts onto the generator case, or through the bushing itself, should the internal seal of the bushing break down over time. This is an example of a complete hydrogen auxiliary system. Everything within the image here, all equipment, all piping, all fittings, contain pressurized hydrogen. They all represent potential leak points and should be part of your regular hydrogen leak monitoring system. In closing, hydrogen is an excellent cooling gas, but if it is not handled properly, it can be very dangerous. Hazardous areas are present in power plants and require specialized equipment and processes to be followed. Generator purging procedures must be up to date, well written, and adhered to. Online hydrogen purity monitors are mandatory and need to be properly maintained. And all power plants should have procedures for locating and repairing hydrogen leaks. It's all about safety, risk mitigation, and reliability. Thank you, Russell.
All right. Thank you, Gus, for that presentation. That was a lot of great information in a short amount of time. Thank you so much for that. It is time for the Q&A portion of today's webcast. If you do have a question for Gus, please click on the Ask a Question button in the presentation window. You can type your question there. And it looks like we have quite a few questions already. So let's go ahead and get started. Gus, I think we'll start with question number 10 in our queue. And the question is this: can nitrogen gas be used as a purging material rather than CO2?
Yes, Russell. We've found recently that nitrogen has become a popular selection in place of CO2 as the purge gas. The challenge there is for some of the hydrogen purity meters that are on the market today, they can't differentiate between nitrogen and air, because particularly when you talk about both density and the thermal properties. So they're so close to one another that those technologies can't differentiate between the air and nitrogen when you're purging the generator of the air using the nitrogen. So another method has to be employed to detect the full changeover from nitrogen to air or air to nitrogen.
Mm-hmm. Very good, very good. Let's move on to the next question. Our person is asking question number 7 in our queue. What is the preferred material of construction of hydrogen piping and valves? What are the materials to be avoided other than bronze?
Well,
does that make sense?
It kind of makes sense. The preferred material is stainless steel, particularly a 300 series stainless steel. That's the most, I guess it's the material that is the least affected by hydrogen gas. I know it's an expensive selection, and a lot of people choose to use carbon steel, particularly because of the cost. They use thicker wall carbon steel for the pipe work and let the degradation of the carbon steel over time be factored into the wall thickness. But if you want to ensure the protection of the equipment that attached to the piping, the stainless steel option is always preferred because then there will be no breakdown of the stainless steel that would result in any damage to the other equipment attached to the pipe. And then the comment on bronze, I don't quite understand that comment. We mentioned bronze in the presentation. as it refers to a material to be used as a material in the non-sparking tools. The non-sparking tools are made of bronze and therefore don't cause a spark when they're coming into contact with steel, stainless steel, or other material during the maintenance on that equipment.
Mm-hmm. Very good. Well, perhaps we can clarify that question offline when we get done here. Let's move on to another question. This is a very short question, and I guess it's a clarification type of question. It's question number 6. What is P&ID, simply put?
I'm sorry about that. I didn't mention that before. P&ID is referred to as piping and instrumentation diagram, or otherwise referred to process and instrumentation diagram, depending on the standard of the company you're working with. It's basically the drawing that shows all the piping and all the instrumentation and equipment attached to that given subsystem that's referred to on the drawing. I
see. All right, very good. Let's move on to our next question, and let's move on up to the question number 2. And the question is this: regarding the hazardous area discussion, what's the difference between a zone and a division? And the person asking this question says that they have equipment in their plant rated for Class 1, Division 1. Does that make sense?
Yep, that's a good question. The zone classification is following the newer standards that were applied. Earlier on, I think we got to go back 10 or 15 years, particularly in the U.S. and Canada. They broke the area classification down into 2 divisions, Division 1 or Division 2. They came out with a rewrite of the standard, and they took the Division 1 and separated it into 2 other classifications. That's where the Zone 0 and the Zone 1 came to be. The next comment, the Class 1 Div 1 equipment, that's where you'd have to get into some better understanding, because Division 1 now falls into 2 categories, either Zone 0 or Zone 1, and you'd have to discuss with the OEM who provided that equipment if it's applicable for use in Zone 0 or Zone 1, but it's certainly applicable for use in Zone 2. A Class 1 Div 1 piece of equipment is rated at a stricter classification than Zone 2 is.
Okay, very good, very good. Let's move on to question number 3 in our queue. And the question is this: with regards to the intrinsic safety protection principle, how do you properly select which barrier to use with a given piece of intrinsically safe instrumentation?
The best way is to read the manual, and a lot of times the manual gets tossed aside, but that's within the manual of the piece of equipment. They define key parameters, key electrical parameters associated with the voltage, the current, and the total power consumed of instrumentation. The different barriers on the market today are designed specifically to match up with those parameters that are marked out in the manual. So you can match up using that. A lot of times you can, when you get the piece of equipment, they have a recommended selection of barriers to use with their piece of equipment, so you can match it up that way quite easily. Okay.
Very good. Let's move on to the next question, and let me point you to question number 5. The question is this: is there any limit of dew point of hydrogen in the turbo generator on the negative side?
In our experience, we haven't come across any recommendation from an OEM that indicates that there's any negative, using negative twice in the answer here, that there's any drawback making the generator further negative in dew point. That's been Environment One's experience to date. We certainly know that dew point that is greater than 0, so a positive number, is certainly of concern for the different failure modes associated with the hydrogen-cooled generators.
All right. Very good, very good. Let's move on to the next question. The questions keep rolling in. Let's move on to question number 9 in our queue. And the question is this: what frequency is recommended for portable instruments and the H2 purity meters?
Again, that's going to be OEM to OEM specific. And to what degree of accuracy do you want to maintain your purity measurement? So a lot of times the purity meter manufacturers will post a drift rate that their unit will be rated within, and then they'll have some recommended calibration frequency listed in the manual. Environment One's recommendation is to calibrate twice a year. Therefore, you maintain the most accurate purity reading on your most critical measurement on your hydrogen-cooled generators, your hydrogen purity meter.
Yeah. All right, very good. Let's move on to another question. This question actually is not in the queue, but the question is this: how often should the SOP be reviewed and updated? That makes sense?
Sure. Yep. I'm assuming they're referring to the purging SOP, the generator purging SOP, which we referenced. Certainly, prior to any planned outage, you'd want to review the SOP, compare it to the P&ID and the installed equipment to make sure they all match. Certainly, if you're doing maintenance and upgrades within your hydrogen auxiliary system, the minute you make a change at your processes and your plant should be the minute a change is made to your hydrogen auxiliary equipment, you should review and change your generator purging procedure and your hydrogen auxiliary ID at that point in time.
All right. Let's move on to question number 12, and the question is this: what is the required purity of hydrogen? Is it 99.9999%?
The hydrogen that's delivered to the generator is typically 4 nines, 99.99. The purity of the hydrogen within the generator, each OEM has a prescribed limit they'd like to operate at based on the design of their seals and what the known leakage rates are. But in application standard we see is generally greater than 95%, with alarms in and around 95% as warnings on the equipment that's installed.
All right, very good. Let's move on to question number 13. In the last photo of the hydrogen equipment in your presentation, there was a light fixture above the panels. Does that light fixture also need to be classified?
If you go back to the earlier slide in the presentation where there was the zone bubble around the piece of equipment that there was in discussion, if you stack up all those zone 2's equipment and it extends to the area where the light is, the answer to that question is yes. From the picture that's here, one, I can't tell if that is an EX rated light, and two, with the proximity to the first pipe work there, I can't tell if that's within the zone of concern for a zone 2 rating on that. But it's a very good question. The conservative answer of me would be certainly you'd want that light to be rated for the classified area. But again, the assessment of all the pipe work for that plant would mark it out accordingly.
Very good. Let's move on to question number 15 in our queue. The question is this: what are some items to consider when setting up a quick purge system to prepare for emergencies that will require the hydrogen to be purged by CO2 very quickly?
That's a good question, and it's a rather complicated question, and it goes back to how your CO2 is delivered into the generator. One of the properties of CO2 is that when it is expanding, it actually can freeze the pipework and other materials that come into contact with it. So if you do not have a device referred to as a CO2 vaporizer or CO2 expansion heater on your CO2 delivery system, you may be limited in the maximum flow of CO2 based on your pipe size and any restrictions due to valving on the delivery of the CO2 to the generator. If you try to deliver the gas faster than a certain rate, you'll freeze up the piping and you'll result in a restriction in flow of CO2 to the generator. So that becomes your first consideration is, do you have a CO2 vaporizer to ensure that the CO2 doesn't freeze up and can maintain a large flow of CO2. From there, it's the size of your pipework and the total size of the generator. And if you, most generator OEMs have a maximum purge rate that they would recommend based on the piping sizes and the header sizes within them.
Okay, let's move on to question number 20 in our queue, and the question is this: what is the recommended safe zone in feet around the generator?
That's going to come down to the pressure that generator is operating at and the local codes and standards for the country that the generator is operating in. So those are more specific to the generator installation itself and the pressure, maximum pressure that it's rated to.
Mm-hmm. Very good. Let's move on to another important question, to question number 23. And the question is this: what are the specific applicable standards associated with the hydrogen zoning and equipment labeling? What organization publishes those standards?
All right, so again, the standards that apply will be specific to the country that your equipment's installed in. So here in the United States, the UL standard, UL-60079, is the classification standard for hazardous area. And then within that, there's sub-standards specific to the type of protection method that's applied, like we reviewed earlier in the presentation.
Mm-hmm. All right, very good. Let's move back up to question number 22. And the question is this: is it typical to put hydrogen piping underground since the storage locations are sometimes remote?
The answer to that question is yes. Probably more than half the time we come across that the hydrogen piping is underground between the bulk storage facility and the delivery system within the power station. And that does pose some concerns, both because of seismic concerns for shifting and potential damage to the pipework, and then also what additional detection methods do we have to use when we talk about leak detection. As we discussed in the presentation, if you have underground hydrogen piping, that brings into play a different layer of concern and methods to apply for leak detection for underground hydrogen piping.
All right, very good. And I think we have, appears we have time for one final question. Let me point you to question number 26 in our queue. And the question is this: how do you calculate the dimensions of various zones or divisions? What are the codes to be consulted?
Similar to the previous question, the codes are specific to the country where the equipment is installed, and the calculation is based on the pressures within the equipment, the maximum potential leak path, maximum potential size of the leak path, and then the standards that apply will be specific to the country. So the United States, we have the UL standards, and they also refer to the NEC, National Electric Code, or NFPA. What we can do is we can get a little more specific in our responses that we'll post via the Excel. We'll take all these questions that came through today, and we'll put out more detailed responses to each one that will be available to everybody who's logged in today.
All right, very good. Thank you, Gus. Thank you very much for your time today. I think we'll wrap it up there. Thanks to everyone. You've been tuned into Hydrogen Safety, Best Practices for Securing Your Most Valuable Assets, brought to you by Power Engineering Magazine and E1 Utility Systems. On behalf of Power Engineering, I would like to thank today's speaker for his time and willingness to share his expertise. This presentation will be archived within 24 hours and can be accessed from the home page at the Power Engineering website. That's www.power-eng.com. A reminder email message for the archive will be sent to all registrants, complete with a direct link to the archive. We thank you so much for joining us today, and we look forward to seeing you again at future Power Engineering webcasts. Take care, everyone, and have a great day.
Okay.